Hello students, myself Professor Ankur. I welcome everyone for the GATE theory session on analog circuits. Today we are going to cover an important topic from the topic of power amplifiers. We will be covering Class B Power Amplifier in our third session on power amplifier. Let's start with the session now. So before we start with Class B Power Amplifier, we need to go back and understand what are the basics of Class B. So in Class B amplifier, as all of us are aware, the Q point is being set at the zero level on the DC load line. The angle of the conduction is going to be 180 degree, that is half cycle output. And for achieving this, we have to go for a concept called as zero biasing. The efficiency of the Class B will come around 78%. The most important point to remember here is, whenever we give a full cycle to a Class B circuitry, the Class B circuitry will amplify only one of the half cycle. And hence we can say that the angle of the conduction is going to be 180 degree. And to ensure that such an operation is being happening, we can say that zero biasing concept is being applied. So it's as good as the transistors will be having zero biasing for the input terminal. So there's a confusion regarding, if I give a complete cycle and you're getting only a half cycle, as per our understanding, we always want a full cycle at the output. So how do you get the full cycle? So for that, we require two half cycle. And every transistor is now going to conduct for only a half cycle. Hence, we can say that two transistors will be utilized in Class B circuitry, where each transistor will conduct for one half of the AC input. Normally, we can say one NPN and one PNP transistors are used with balanced rating in Class B configuration. Whenever we use a NPN transistor and a PNP transistor, the concept of arrangement is also called as complementary symmetry. Complementary is with respect to the concept of NPN and PNP. Symmetry is with respect to the ratings of the device. Generally, it is under push-pull configuration, where the AC input signal pulls one transistor in the on state and pushes the other transistor in the off state. Since the biasing is absent for the Class B circuitry, the transistors will turn on or off depending on the status of the input signal applied to it. And that's the reason AC signal will control the on state and the off state behavior. And such a behavior is also called as a push-pull configuration. So these are the basic features of Class B power amplifier, where normally you will have two transistors in the circuitry. Preferred one will be complementary symmetry logic, and it is being configured under push-pull configuration. So if you observe, this is a transformer coupled Class B power amplifier, where the input is given to the input section of the transformer, which will be coupled to the secondary. The transformer utilized here is a center tap transformer, and because of this, the coupling effect from the input side to the top section of the transformer will be in phase, whereas coupling effect from the input side to the bottom section of the transformer will be out of phase. Due to this, we get operation same as a complementary symmetry or push-pull operation. Since we are using two transistors of the same type, one is NPN and the other one is also NPN, we need to ensure that both the transistors are actually operating in independent half cycle. And that is the reason the center section, where we are actually using the first transformer, the first transformer is a center tap transformer. The center tap transformer will ensure that when the positive cycle reaches input of first transistor, that time negative cycle will reach the input of the second transistor. And when the negative cycle reaches the input of the first transistor, that time positive cycle will reach at the input of the second transistor. So overall, if you observe, only one of the transistors will be on, the other transistor will be in the off state. And secondly, the direction of current IC1 and IC2, as you can see in the figure, is shown clearly. And the resultant current in the primary of the second transformer will be IC1 minus IC2. So it will be coupled to the secondary and then it will be given to the load. So if you observe the operation carefully, you can see that the transistors will be on in a specific half cycle only, and the status of the on and off is being controlled by the input signal. That is the reason this configuration can be called as a push-pull configuration. The second configuration that you can see here, it is a complementary symmetry push-pull Class B power amplifier, where you can see the center section where there are two transistors being used. One is NPN, another one is PNP. The input is given to the base of both of the transistor, and we are using two supplies plus VDD and minus VEE. The emitter terminals of both the transistors are shorted and connected to the load where we can get the output. Now, whenever we talk about the operation of the signal, you can see the representation of input versus output. You can clearly observe that we got the first half cycle output because of Q1 on and Q2 off. And we got the second half cycle output because of Q1 off and Q2 on. And the third cycle for Q1 on and Q2 off. So if your observation is sharp, here the two transistors are of the complementary family. One is NPN, other one is PNP. Since they are being fabricated with same parameters or matching parameter, they will be called as complementary symmetry. The entire operation of the circuitry is controlled by the status of the input cycle, because the input cycle will decide which transistor will be on and which transistor will be off. So automatically when Q1 is on, Q2 is off, and when Q2 is on, Q1 is off, and hence the name push-pull configuration. Since the transistors are conducting only for half cycle, we can say it is Class B power amplifier. So hence the name complementary symmetry push-pull Class B power amplifier. Now we are discussing the operation in the independent half cycle. So when you see the independent half cycle, suppose if I consider the positive half cycle of the AC input that will be applied to base of both the transistor. But because of this, the positive voltage will make Q1 in the on state and Q2 in the off state. And hence we get a positive cycle at the output. And during the negative half cycle, the Q1 transistor JB junction will be reverse bias, leading to Q1 in the off state, but Q2 will be in the on state because it's a PNP transistor which requires a negative voltage for base emitter junction to become forward bias. And that's the reason you will find Q1 off and Q2 on, and automatically you will get a half cycle at the output. When you merge the combination of both the half cycle, you get a complete full cycle. So overall effect, if you see, the effect of amplification is basically contribution of two independent operation in the first half cycle by Q1 transistor and in the second half cycle by the Q2 transistor. So here you can see the behavior of or operation of one transistor, where we can get, when we are giving a complete cycle at an input, we are getting only a half cycle at the output. So when the input was a complete sine wave, you got IC1 in the first cycle and in the third cycle, whereas IC2 because of the Q2 transistor will be in the second and the fourth cycle. So when you merge the operations of IC1 and IC2, we get a resultant collector current. So now when I talk about the value of PDC, that is a DC power supplied to the transistor, it will be twice of VCC into IC sat by V pi. And whenever we talk about PO, that is the AC output power, it is VCC square by twice of RL. So when we talk about calculation of efficiency, which is the ratio of output AC power by input DC power into 100, solving this, you will get the value as 78.5%. Now, if you compare this operation or performance with respect to Class A family, the Class A family was having a efficiency from 25% to 50%. Whereas in the Class B, you can see the huge improvement in the efficiency as it has gone up to a value of 78.5%. So this is the biggest advantage of Class B circuitry, where they will be using, or you can say, two transistors, but also giving you better performance with respect to the efficiency parameter. Now, the only drawback that is being faced by the Class B circuitry is defined as crossover distortion. As everyone is aware that the transistors will be turned on depending on the input signal. So the input signal is responsible for making the base emitter junction of both the transistors Q1 and Q2 forward bias. But all of us are aware a junction can become forward bias only after a specific voltage is being applied to it. So it's like a behavior similar to a diode, where a diode will become forward bias only when you apply a voltage greater than or equal to 0.7 for operation. On similar lines, if I want a transistor to go in the on state, the voltage applied at the input or the base terminal of the amplifier needs to be greater than or equal to at least 0.7. So that's the reason you will find that during the operation of the output, you will find that the lever required from VBE and minus VBE is a patch where the amplifiers are in the off state, and if the amplifiers in the off state, there will be no amplification. And that's the reason when you see the lower figure, you can see a gap in between. So this gap is basically loss of energy, and this effect is called as crossover distortion. Whenever the signal was transiting from positive cycle to negative cycle and negative cycle to positive cycle, that time during the transition point, you will find that the output will be off because Q1 and Q2, both of them are in the off state. And that's the reason you will find loss of information or loss of energy. This concept is called as crossover distortion. Whenever the signal is crossing over the reference line, we get distortion in the output, hence the name crossover distortion. So what is the solution for this problem? The only solution for this problem is to ensure that when the input signals are applied, the transistors are in the on state. Implies if I want to turn on a transistor, if it's a NPN transistor, I need to provide somehow a potential of zero point 0.7, and if it's a PNP transistor, at the base we need to provide minus zero point 0.7. So this will be done using external biasing, and that's the reason as an improvement in class B, we go for a modification called as class AB. Because if we remember the definition of class A, the class A had biasing. In class B, there is zero biasing. So now if we decide that we want to give a small amount of biasing for operation so that we can avoid crossover distortion, this concept is called as class AB power amplifier, where a minimal amount of potential will be applied to the basis of the transistors so that they are in the on state when the input signal is being applied, so that we can avoid the loss of output or crossover distortion. So this is the concept of class B and class AB power amplifier.